Hi, welcome to Computer Science Explained. In this video, we will talk about number systems in general and we'll make a detailed analysis of the base 10 number system and the base 2 number system. The simplest system of counting is the tally-mark system. We can write 1, 2, 3, 4, 5, 6, and so on. Very easy, right? But how long will it take to read this number? And how long will you write 1 million? And how much space will it take? And how many mistakes will you make during the process? The Roman system makes counting slightly easy by grouping several tally marks. For example, a group of 5 tally marks is represented by the letter V, and so on. This is number 38 in the Roman system. Not very concise. Writing millions and billions will be a disaster. Of course, we can assign a particular symbol to each number, for 10, for 11, and so on. It will be a very concise notation. But can you remember several millions of symbols? And can you imagine a keyboard for this system? And the numbers are not restricted to several million. The numbers can increase up to infinity. In general, all number systems can be divided into two groups, non-positional and positional. In non-positional number systems, all positions have equal weight, and the position of a digit does not affect the final number. This group of number systems is very inefficient. We already discussed all problems of this group. In positional number systems, all positions have different weights. The position of a digit affects the final number. This group of number systems is very efficient. This group includes all the base number systems, starting from the base 2 number system. Of course, including the base 10 number system. In positional systems, weight of each position to the left is a certain number of times greater than the weight of the previous position. The certain number equals the base, so the weights of the positions grow exponentially from right to left. Next, we will talk only about positional number systems. But first, let's recall exponentiation. For example, 2 to the power of 3 equals 2 times 2 times 2 and equals 8. So we have 3 repeated multiplication of 2. 2 is a base and 3 is an exponent. So the general rule is base to the power of exponent means repeated multiplication of the base as many times as exponent is. Now let's consider the base 10 number system. Let's take for example number 4107. Digit 7 occupies the position of ones. Digit 0 occupies the position of tens. Digit 1 occupies the position of hundreds, and digit 4 occupies the position of thousands. Let's write out explicitly the weights of the positions as numbers. 1 for position of ones, 10 for position of tens, and so on. The positional base 10 number system interprets our number as 7 times 1 plus 0 times 10 plus 1 times 100 plus 4 times 1000. Now let's generalize our knowledge about the base 10 number system and build a scheme for any positional number system. In the base 10 number system, we have 10 digits from 0 to 9. These digits can occupy these positions. So the position of ones should be occupied by exactly one digit from 0 to 9. For the position of tens, the same story, and so on. Please pay attention that for any positional number system, including base 10, the first digit is always 0. And the last or maximum digit always equals the base minus 1. For the base 10 number system, 9 equals 10 minus 1. The number of digits always equals the base. In our case, base is 10 and the number of digits is 10. Now let's consider the most important method of the calculation of the weights. So for the base 10 number system, we have a sequence of weights 1, 10, 100, 1000 and so on. 1 equals 10 to the power of 0. In the general case, the weight of the extreme right position should be calculated as a base to the power of 0. Any number to the power of 0 equals 1. So the weight of the extreme right position in any number system always equals 1. In the second from the right position, for the base 10 number system, we have weight 10. 10 equals 10 to the power of 1. In the general case, in the second from the right position, weight equals base to the power of 1. Since each number to the power of 1 equals itself, weight equals the base. In the third from the right position, for the base 10 number system, we have weight 100. 100 equals 10 to the power of 2. In the general case, in the third from the right position, weight equals base to the power of 2. The pattern of this sequence will continue for each position to the left. In the base 10 number system, exponents of the weights start from 0 and are increased by 1 from right to left. Values of the weights start from 1 and are multiplied by 10 from right to left. In the general case, for any positional number system, exponents of the weights start from 0 and are increased by 1 from right to left. Values of the weights start from 1 and are multiplied by the base from right to left. Now let's consider the base 2 number system. We will apply the general scheme for the base 2 number system. We need to substitute the base with 2. In the extreme right position, weight equals 2 to the power of 0, which is 1. In the second from the right position, weight equals 2 to the power of 1, which is 2. In the third from the right position, weight equals 2 to the power of 2, which is 4, and so on. In the base 2 number system, exponents of the weights start from 0 and are increased by 1 from right to left. Values of the weights start from 1 and are multiplied by 2 from right to left, giving us the sequence of weights 1, 2, 4, 8, and so on. In the base 2 number system, we have two digits 0 and 1. These digits can occupy these positions. I marked the digits of the base 2 number system with magenta color. The position of 1s can be occupied by the digit 0 or 1. The position of 2s can be occupied by the digit 0 or 1, and so on. Please pay attention that 0 is the first digit, and the last digit equals the base minus 1. So in our case, 1 equals 2 minus 1. Please pay attention that the number of digits equals the base. In our case, base is 2 and the number of digits is 2. Let's, for example, convert 1001 from the base 2 number system to the base 10 number system. First, we arrange from right to left all digits in corresponding positions. Then, we multiply digits by the weights of corresponding positions and sum up intermediate results. So 1001 equals 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1 and equals 9. All positional number systems comply with the same general scheme, but the base 2 number system is, in some sense, unique because of its set of digits 0 and 1. These digits can be interpreted as taking corresponding weight to a resultant number or not taken. For other positional number systems, we can take more than one corresponding weight. For example, in the base 10 number system, we can take up to 9 corresponding weights. Now let's, for example, convert the number 13 from the base 10 number system to the base 2 number system. To do this, we need to fill with digits 0 and 1 these positions in such a way that the sum of these positions will give us 13. We don't need to try all possible variants of zeros and ones. We can move from left to right each time trying to fill a position with the maximum digit. Since this is the base 2 number system, the maximum digit is 1. If, in some step, the sum of the product of digits that were already taken and corresponding weights is greater than the target number, we need to decrease the digit by 1. In the base 2 number system, from 1 to 0. And then continue the same steps till the extreme right position. So 13 equals. Let's try to put digit 1 in the 16th position. 16 is already greater than 13, so we can put only 0 in this position. Next, let's put digit 1 in the 8th position. 0 plus 8 equals 8, which is less than 13, so we can continue. Let's put digit 1 in the 4th position. 0 plus 8 plus 4 equals 12, which is less than 13, so we can continue. Let's try to put digit 1 in the 2th position. 0 plus 8 plus 4 plus 2 equals 14, which is greater than 13, so we can put only 0 in the 2th position. Let's put digit 1 in the 1st position. 0 plus 8 plus 4 plus 0 plus 1 equals 13. We obtain the required result. Now we can delete all consecutive zeros from the left of our number, because these zeros don't matter. In our case, we have one such zero. The final result is 1101. So our algorithm of moving from left to right and trying to put the maximum digit works perfectly. But how far to the left should we start this movement? To find out this, we need to start from the extreme right position and move to the left, comparing weights with the target number until the weight will be greater than the target number, and then return one step to the right. So in our case, we compare 13 and 1, 13 and 2, 13 and 4, 13 and 8, 13 and 16. 16 is greater, and we return one step to the right. Starting position is the position of eighths. We don't need to start from the 16th position, because 16 is greater than 13. I started from the 16th position in the example to show this. Now let's consider shifting each digit one position to the left. This is equivalent to writing 0 to the right of the number in any positional number system. And as a result, the number will be base times greater. So in the base 10 number system, it will increase 10 times, and in the base 2 number system, it will increase 2 times. Let's take 359 as the base 10 number system example. On the left is the number before the shifting, and on the right will be the number in process and after the shifting. Initially, digit 3 was in the hundreds position, so it represented 300. But after the shifting, digit 3 is in the thousands position and represents 3000, which is 10 times more than previously. The same story for another two digits, 5 and 9. After the shifting, each starts to represent 10 times more. If each part is 10 times greater, the whole is also 10 times greater. Please look attentively at the calculations. Now let's consider an example of left shifting number 101 in the base 2 number system. On the left is the number before the shifting, and on the right will be the number in process and after the shifting. After the shifting, each digit is situated in the twice more valuable position than before the shifting. If each part is 2 times greater, the whole number is also 2 times greater. Please look attentively at the calculations. I hope everything is clear. Thanks for watching. See you next time.